Welcome to this explainer. Today we are diving into the absolute foundational logic behind how predictive AI and machine learning models actually learn, and honestly, why they sometimes totally fail. We're going to explore a really fascinating core concept called the bias-variance trade-off. Basically, this is the art of balancing the error from erroneous assumptions with the error from sensitivity to training set fluctuations.
So let's kick things off with a pretty fundamental question. If machine learning is just so incredibly advanced right now, why does it still struggle with brand new, unseen data? I mean, why do models that look absolutely flawless in the lab completely fall apart out in the real world? Well, it all comes down to a mathematical tug-of-war that literally every single algorithm has to play.
Here is our roadmap for today. We'll hit the machine learning dilemma, define bias and variance, compare underfitting versus overfitting, break down the trade-off itself, learn how to tame it, and finish up with why this all actually matters.
Section 1. The Machine Learning Dilemma. Picture an AI that's trying to guess someone's age just by looking at a photo. Now, if this model stubbornly guesses 30 years old for literally every single person, it's making a massive, super rigid assumption, right? It's completely inflexible. But flip that around. What if its guesses are just wildly all over the place, like guessing 12 for one photo and then 85 for a nearly identical one? Now it's way too sensitive. Both of these extremes give us terrible predictions just for completely different reasons.
Moving on to Section 2, defining bias and variance.
So let's get into the terminology. Bias is the error that comes straight from those rigid, erroneous assumptions we just talked about. When a model has high bias, it's inflexible, it's consistently off-target, and totally misses the underlying trend of the data. Think back to that model always guessing 30. It consistently misses the mark by a very predictable, expected amount.
And on the flip side, we have variance. Variance measures how wildly a model's predictions swing just from being exposed to different sets of training data. Imagine if your model changes its entire internal logic just because you fed it a slightly different batch of training photos. That means it has high variance. It's way, way too sensitive to all the random noise present in the data.
Section 3. Underfitting versus overfitting.
This perfectly illustrates those two extremes. Underfitting happens when your model is just too simple to learn the data. It's got high bias and low variance. It's kind of like trying to describe a highly complex masterpiece using only 2 or 3 words. Overfitting, though, occurs when a super complex model basically memorizes the training data, including all the useless random noise, instead of learning the actual pattern. That gives us low bias, but incredibly high variance. It'll absolutely ace the training test, but totally fail the second you show it something new.
Notice how, on a U-shaped error curve, as you increase the complexity of the model, moving left to right, that blue training error just keeps dropping. The model is literally memorizing the data. But look at the orange test error. That represents how it actually performs on unseen data. It hits this perfect sweet spot, and then eventually skyrockets as overfitting completely takes over.
All right, Section 4. The Bias-Variance Trade-off. Here's the thing. The math actually proves you cannot escape this dilemma. A model's total expected loss breaks down precisely into 3 components: bias squared, plus variance, plus an unavoidable, irreducible constant noise factor. Since you obviously can't control the inherent noise of the universe, your one and only job is to balance the bias and the variance. If you try to push one down, the other naturally, unavoidably wants to pop right back up.
You can really visualize this trade-off in action right here. Over on the left, we've got this erratic, overly complex model with super high variance. Those red lines are just swinging wildly, desperately trying to hit every single noisy data point. But contrast that with the right side. That is an optimal, smooth, regularized fit. It completely ignores those wild fluctuations and elegantly captures the true underlying trend in green.
And this right here visually defines our Goldilocks sweet spot. Notice how the blue line, representing squared bias, is falling as the complexity goes up, while the red variance line is starting to climb. That magenta line on top? That's their sum, the total expected error. The absolute minimum point of that magenta curve is exactly what we're looking for. It is the precise moment where the error from erroneous assumptions and the error from data sensitivity are perfectly balanced.
Section 5. Taming the trade-off.
So, how do data scientists actually tame this thing? Well, we rely on a few really clever mathematical techniques. The first is regularization, things like L1 lasso or L2 ridge regression.
This literally penalizes the model for being too complex, essentially pulling its parameters closer to zero. It intentionally bumps up the bias just a tiny bit, all to achieve a massive stabilizing drop in variance. Another brilliant trick is bagging, or ensembling. By averaging out multiple independent datasets, you can divide the overall variance by the exact number of datasets you used, and you do it without increasing your baseline bias at all. It's a real game changer.
And finally, Section 6, Why this trade-off matters.
As this excerpt from financial machine learning literature points out, we can actually intentionally manipulate this trade-off. There are times when we absolutely want to leverage highly flexible, complex models. We knowingly accept some variance, a little bit of noise in our estimates, because the huge payoff is a much more accurate approximation of a complex truth. We are actively minimizing our bias.
And in high-stakes, fast-moving fields like algorithmic trading, finding that exact balance translates directly into optimal economic outcomes. Think about it. If your model underfits, you're going to miss the subtle market signals. But if it overfits, you end up trading on pure noise and losing money. Nailing that sweet spot is the direct driver of real-world profitability.
Which leaves us with this final thought to wrap up our explainer today. Knowing that real-world data is infinitely complex, and that inherent noise is just completely unavoidable. Will we ever find a truly perfect model? Or is the entire field of machine learning simply an eternal, beautiful balancing act between bias and variance? Keep that in the back of your mind the next time you see an AI make a seemingly basic mistake. Thanks so much for tuning in, and keep learning.